Good afternoon, everybody. Welcome to another exciting afternoon of Organic Chemistry with your host, me, Dr. White. Excuse me. Hope you all had a nice weekend. I was busy and I'm finally sleeping normally again. My back is getting better. Good thing. All right, a couple things. First of all, as you all know, I handed back, or I posted the scores for test number 3. I also sent you emails with your individual answer scores, because I can't do that like I would normally in a classroom, mark them, hand back your test, but I found a way I can do almost similar. What I'm going to do today, give you a heads up on things we're doing today. 1, I'll be going through test number 3 answers, and I will be eliminating it from the videotape. If you'd like to see them again or talk about it, come to my office hours or stay after class. Next, we'll finish up the lipids chapter, and then we'll get into some really fattening stuff, carbohydrates. So that's the game plan for today. But first, it's winter. Nothing like nice hot tea from the Republic of Tea. Also, coming attractions, before Wednesday's class, I will be posting, are you ready for this? An extra credit project that's worth 10 points. That's like getting 10 more points on one of your tests if you do well on the extra credit, which everybody should. If you do it, it's totally optional. And I'll be posting it probably sometime tomorrow, and I'll talk about it on Wednesday. And that's test number 3. Now, a question I would have if I were in your shoes, I don't know if I fit in your shoes, my feet aren't that small, but I wear 11.4E. Oops. Anyways, question I would have is, what grade am I getting now in this class? And that's a good question. Let's go through how you figure that out. Everybody see the whiteboard? Plain white screen, thank you. All right, there are 2 methods. I can spell. Take the sum of your 3 highest test score, or your 3 test scores, divided by 3. You'll get a number X. If X is 100, 99 to 100, it's an A. If X is 80, 89, B, 70, 79, C, 60, 69, D, and 59 or less F. That's the percent breakdown for grades that I have in my syllabus. Just go ahead again. What is X? Determine that. Now, method 2, take the sum of your 2 highest of 3 test scores, divide that by 2, you'll get a number Y. And if Y is 90 to 100, you're getting an A. If Y is 80 to 89, B, 70 to 79, C, 60 to 69, D, 59 lower F. Now, there's still a lot of points left. We have test number 4, which will be 100 points. Actually 105, I'll have 5 bonus points. And the final exam, don't get scared when I do this, will be 210 points, and I'll have 10 bonus points. Because it's like 2 tests. By the way, why did I say don't get scared? Because yes, my final will be comprehensive the whole semester. However, I've been teaching Chem 170 long enough that on that kind of final, the one I'll write, the average test score for most classes are usually out of 210 points would be about 170 to 180, which is like a few points below an A to an A, which sometimes is even higher depending on the class. Any questions on grading, on tests, on anything but the meaning of life? I haven't figured that one out yet. Going once, twice? All right. Did any of you happen to think about you were making micelles when you were washing your hands with soap and water? Come on, that's organic chemistry. You happen to think that if you looked at the soap you were using, if it was bar soap that came from pig's fat, beef fat, otherwise known as tallow, white grease, yellow grease? I still got some time to work on you. Sorry about that. My Creative Cloud from Adobe has 5 updates. Anyways, think about that. All right. Time for a warning from Dr. White. I'm going to, next couple minutes, I'm going to get into stuff that I can get into because I'm an organic chemist, and this organic chemistry, in no way am I taking any moralistic view, is it right or wrong? It's just organic chemistry. But before then, I want to do a quick little review. And then what I like to review, because this is one of the most important things I'll teach you this semester, is how does soap work? Remember, soap has a structure, I'll show you in a second, that has a hydrocarbon tail, which we call lipophilic or nonpolar, and a polar head. Remember, light dissolves light. You should know. Hold on. I'm going to be real subtle. Subtle? All right, how does soap work? First of all, you should know what is the structure of soap. Soap has a nonpolar tail and a polar head. The most important thing how soap works is light dissolves light. That means polar things are soluble in polar things, nonpolar things are soluble in nonpolar things. I'm not sure, but I think this week's lab, you'll be doing a light dissolves light lab. But anyways, remember water, polar. Dirt and grease, nonpolar, which is why you can't wash dirt off with just plain water, because light dissolved light tells you it's not going to work. Now, again, You should know everything I'm showing you. It's magnifying a little tiny piece of dirt on my hand. And when I take soap and water, the soap, because the nonpolar tail sees dirt that's nonpolar, lines up like this. And a lot of them line up. A lot more than I'm drawing. So it totally surrounds the soap molecule 360 degrees, and we call this a micelle. You should know what a micelle is. Now, how does this work? Water, which sees the micelle, says, oh, you're polar, because all water sees is the polar outside of the micelle, the soap molecule surrounding the dirt, says micelle, I'm polar, you're polar, let's go down the drain together. And they do, and that's how the dirt gets off your hands. And if we look at the following, this is what a micelle really looks like. There's been a section cut out so you can see the dirt particle in the center right here. But notice each of these nonpolar tails are heading toward that. The outside is the polar head, and water sees that as polar, and they go down the drain together. You should know that. All right, cover a couple of things. I'm turning the switch off, but I thought you'd like to learn about this. There's certain triesters of glycerol called phosphoacylglycerols or acylglycerols, also known as, ooh, I got to turn something off, hold on. If I don't do this, you'll see squiggly red lines all over my slides when Microsoft Office says, I don't like that. And they're called phospholipids. And phospholipids are found in many places. They have the structure like this. These are one of nature's surfactants. Our prime and our double prime can be the same or different. And this is a phospholipid. This is called a zwitterion, and the same molecule will have a minus and a plus charge. But the way this really looks is, this is considered a polar head, and these long R groups here with the carbonyl are your nonpolar tail. So really a phospholipid is this, even though this tail has two components. And it turns out this is very important. Any of you ever hear of phospholipids? I see a couple of you. And you know where you can find one real quick in your house? I'll tell you. Places phospholipids, also called lecithins, are found in egg yolks and soybeans. And one of the things Dr. White has learned personally is the more I eat soybeans, one, the better my thinking process is, my brain works better because of the phospholipids. How that does that, I don't know, I'm an organic chemist, but I do know it's true. And when I eat my soybeans and tofu, I like, but I usually get the soybeans, the green soybeans, otherwise known as edamame, but not in the shells. It's a pain really to try and get the beans out of the shell. Yeah, you can buy it at any supermarket now. I know Target has it, my Valley has it. I haven't looked in Jewel, but they have it. And when I have my daily dose or a couple of times a week of soybeans, by the way, the ones that are already shelled, you boil them for 5 minutes. I think that's just kill any bacteria in there. And then take them out. What I do is let them cool. Then I put them in Ziploc gallon freezer bags. I make sure it's flat layer. And I freeze them. Take that out of the freezer, crack off a part, throw it in a soup or whatever, heat it up with other stuff, and it's good to go. By the way, those soybeans have almost no taste to it. So however you flavor it, that's how they taste, which is not bad. Now, the other place you can find lecithin, otherwise known as phospholipid, is egg yolks. Now, they make industrially, and also for cooking, lecithin, which is a phospholipid. I bet you don't know what color that is. Yellow. That's what gives the yellow to egg yolks. And if you're not familiar with it, how do you make mayonnaise? Any mayonnaise is really mostly oil and water. But normally these won't mix like in oil vinaigrette dressing. So how do they get it to mix? Well, when you make mayonnaise, the traditional recipe besides seasonings are the egg yolk, or really egg yolk. I don't think I spelled that right, but whatever. Water and vegetable oil. And the less, yes, I did spell it right, it's up here. And the lecithin in the egg yolks, the surfactant, helps bring the water and oil together and keeps it together. The next time you use mayo, by the way, I like Hillman's mayonnaise. I like it too much. My sister hates mayonnaise, period. Well, what can I say? She's got good taste in other things, but not liking mayonnaise. And, or she doesn't like chemistry either. What can I say? But she had a bad chemistry teacher in high school. Mayonnaise is held together because of the surfactant, lecithin, that's in the egg yolks you use to make mayonnaise. All right. Long time ago, beginning this chapter, we talked about lipids. There's two types of lipids, saponifiable and non-saponifiable. The saponifiable we talked about as saponifiable lipids, fats, and oils. What are the non-saponifiable? Remember, those are molecules that come from things that were alive that when you react with base and water, alkaline conditions, give no reaction products. So what are they? They are the steroids. The steroids are lipids based on this ring system. These are called fused rings where they share common carbon. All steroids, and by the way, you know steroids by another name, and that is your hormones. And all your hormones have this ring system. Now, I expect you to know how to draw the ring skeleton of a steroid. And let me show you how to do it. 6-membered ring. Right next door, 6-membered ring. Up here at 12 o'clock high on this 6-membered ring, another 6-membered ring, and then right next door, a 5-membered ring. And all hormones have this ring skeleton in them. 3 rings, 4 rings, I mean, I can't count. A, B, C, D. That you don't have to know, But if you're into steroid count nomenclature and discussions, those are the identification for those rings. The UPAC names for some of these are woo, interesting. All right, how are we doing time-wise? Good. All right, hang in there while I do something I do always in class now. Hang in there. All right, once again, I'm getting some neat stuff now, and no way am I taking a moralistic view, but it's organic chemistry, so I can talk about it. All right, when we talk about, and the switch is off now, but still it's interesting. We talk about the different steroids. You should see on here testosterone. And testosterone, now that you know organic chemistry, has the 4-ring skeleton, 6, 6, 6, 5. And then here I have a ketone, carbonyl, oxygen. I have a double bond. I have an alcohol up here, carbon with. Now these wedges tell you stereochemistry, which I'll teach you a little more about next chapter. But at the end of every line is the methyl group. So there's a methyl group here and here. It's coming towards you. This hydrogen is going back. This is going forward. This is going back. That's called stereochemistry. And this is testosterone. That's the male hormone that's responsible, if I think I'm correct, for my beautiful beard and other nice things on my body. And that's testosterone. It's a steroid, a hormone, 6, 6, 6, 5 ring system. All right, let's look at progesterone. Progesterone is a female hormone. And if we look at this, same 4 rings, 6, 6, 6, 5. Like testosterone, we have a ketone here, double bond, but in testosterone, you have an alcohol here. This is a carbonyl with a methyl group here. This is a ketone. So in progesterone, a female hormone, the difference is this structure right here. Why that makes a difference, I don't know. I'm an organic chemist. I'm not a biologist or medical doctor. Now, one of the things you might, have you ever wondered, what's the difference between men and women? Well, if you look at testosterone, progesterone, you'll see men are alcohols and women are ketones. Doesn't that explain everything? Oh, that was awful. All right, let's look at another important hormone. That's called estradiol. And again, it has 6, 6, 6, 5. Here you have a benzene ring plus an alcohol, phenolic ring, and you have an alcohol up here, and you have one methyl group here. Estradiol is the steroid, also known as hormones, that are responsible for a woman controlling a woman's monthly cycle. And various levels in a woman's body tells the woman's body what time of the month it is in her monthly cycle. Now, one of the great advances in all of chemistry, organic chemistry, happened, I think, the late 50s, early 60s. I might be off by 5 years. And that's something that affected our whole planet. And that is the advent of affordable birth control pills. Whether you're for or against them, they have made a great impact on our planet because this gives women who choose to the ability to control their body when they will or will not get pregnant. Now, estradiol to make is extremely expensive. How many women would buy birth control pills if you had to pay $100, $200 a piece? And you needed 30 of them. Lots of them. None. But medical science and organic chemists found that if you made one very similar molecule from cheap intermediates, and this is called a phenyl estradiol, you put a triple bond on the same carbon up here with the alcohol, the rest of it is the same as estradiol. The woman's body thinks, oh, that's the hormone estradiol, and it controls the woman's monthly cycle, which is what birth control pills do. They have different levels of this and there in the pills, so at the right time, when the right number, right day, and the right concentration you consume in the pill, a woman has her monthly period. And that way, even if she's pregnant, it's still, she can't, will not get pregnant, and this is how it works. Now, why is the body fooled by this molecule, which is similar but not identical? I have no idea. But the ability to make it cheaply from cheap intermediates has changed our planet. And that's steroids. Now, what you should know is on a test, if I ask you to draw the structure of the ring skeleton of a steroid, you should know 6-membered ring. Next door, 6-membered ring. At 12 o'clock, 6-membered ring. And next door on the right, 5-membered ring. No, Dr. White's not in the greatest of 6-membered ring drawing days, but you get the picture. And that's estradiol. That's all your steroids, which are your hormones, have this structure. All of them, even stuff that's not a steroid, cholesterol has that structure. And it's a steroid type 6-membered ring. By the way, cortisone has this structure also. And cortisone originally was made from testosterone, and it was extracted from the testicles of slaughtered bulls. And they found a way to make it synthetically. Oh my gosh. Time flies when you're having fun with organic chemistry with Dr. White. It's time for my stretching break. Let's take a 5-minute break, come back at 1:55, and we'll continue on. See you in 5. Time to start again. All right, it's time for a new chapter. And that new chapter is really dangerous because it can be very fattening. And sometimes it could be very sweet. And what's that new chapter? It's carbohydrates. And let's get into it. And as keeping, I'm not going to be doing any new general reactions because I've taught you the key ones you need to know what's going on in your daily life. Now, hopefully you all see chapter 18 with sections of chapter 5. Thank you. All right, this slide, I'm going to turn the slide, the switch is going to be on test off, but I still like to talk about something because there's a misconception. Let's talk about biochemistry. Biochemistry is the study of chemical substance found in your body or things that are alive and the chemical interactions of those substances with each other. Now, here's where people get all bent out of shape. They shouldn't. The functional group chemistry that you learn for organic molecules occurs just the same way in bioorganic molecules. In other words, functional group chemistry going on in your body is the same as what we study. There's no pookie magic going on because it's going on in my body or my stomach. No, but it is more complex molecules, and Mother Nature has done an amazing thing. One of the things I don't have time to get into, but that's steroids, hormones. I just have a mental freeze. But anyways, I got it. Ooh, must be Monday. How many of you have heard the term enzyme? And enzymes are really just Mother Nature's very complex, specialized catalysts. Most of the enzymes are really acid catalysts, like I've been writing H+. Now, some of them aren't, but most enzymes, I believe, don't quote me on this, I'm not a biologist, but they're really catalysts that make a reaction go quicker. Now, in your body and in plants, Mother Nature has some very complex organic chemistry going on, but it still follows the same functional groups we've talked about. And a switch still off, biochemical substance, a chemical found in something that's alive. Click, switch is on. Should you know this for test number 4? And the answer is yes. Let's talk about what is a carbohydrate. A carbohydrate is a polyhydroxyaldehyde, polyhydroxyketone, or a compound that yields such compounds, polyhydroxyaldehyde or polyhydroxyketone, upon hydrolysis. Hold on. And therefore, you should know what is a carbohydrate. Now, below here are 2 examples of carbohydrates. You do not have to know the structures. You should be familiar with it, but you don't have to know them. I will never ask on a test or the final, draw the structure of glucose or fructose. Well, let's look at glucose. Glucose up here, this is an aldehyde. Carbohydrate chemists draw their aldehyde, and so does my software, like that instead of like this. And these are the same. And notice a carbohydrate is a poly, that means many, hydroxyaldehyde. So glucose has an aldehyde and has 1, 2, 3, 4, 5 hydrox groups on carbons, 5 alcohols. Well, in my book, that's many poly, so glucose is a carbohydrate. Now, most of you have been conditioned to think of carbohydrates, like when they say carbo loading, as starches. And it turns out starches are carbohydrates, but the definition of carbohydrates is actually much larger. Now, over here we have fructose. And notice here I have a carbonyl. These are called Fischer projections, and I'll teach you more about it. Every intersection of a line is a carbon. So here's a carbon. There'd be a carbon here, here, here. Obviously, you can see these 2. And if you look at this one right here, what do we have? Carbonyl. Then up here, we have carbons. And down here, we have carbons. And what is this? A ketone. And fructose has 1, 2, 3, 4, 5 alcohol, and therefore this is a polyhydroxyl ketone. Therefore, fructose is also a carbohydrate like glucose. Now, you don't usually think of that, but yes, they are. And I won't ask you to draw ever the structure of fructose, but you should be familiar with it, and you'll see why we do some chemistry with it. Now, there's some carbohydrate classifications which you might use in other classes that you should be familiar with. Most of these, the switch is off, but I'll tell you when I turn it on. And you can have monosaccharide, mono being 1, and that's a carbohydrate that contains a single polyhydroxyl aldehyde or ketone. And glucose and fructose are both monosaccharides, switches off for that. They have, and I don't know if I pronounced it right, I'm not a sugar chemist, oligosaccharides, and those are carbohydrates that contain from 2 to 10 monosaccharide units bond together. Now, there's a special oligosaccharide that you should know. Whoa. And that's a disaccharide. Di, you know, means 2. That's 2 monosaccharides covalently bond to each other. And the most common disaccharide, which is also oligosaccharide, but you should know this is a disaccharide, is a compound called sucrose. That's a common name. You know it as table sugar or sugar. The white little crystals you put in your tea, coffee, or when you're cooking to sweeten things up are disaccharides. 2 monosaccharides bond together to form something that's sweet and tastes good. Unfortunately, it's fattening too, but let's not talk about that now. And then there's polysaccharides. Those are carbohydrates that have more than 10 monosaccharides linked together. And example of this, which I won't, the switch is off for this, but you know one polysaccharide, starch. Starches are all polysaccharides. Now, it turns out something I have purposely not discussed until this point, and I've stayed away from, but now I have to talk about it, and that's something called chirality. Here's our molecular models. Years ago, I bought these or had ECC buy these for labs in 170. After 2 semesters and students hated it with a passion, I dropped the lab. I don't like making students hate things. But in the center is a carbon, and each spoke is a bond. Remember, 4 bonds to carbon. And this would be methane. They don't show hydrogens. And molecules, let's put 2 together. Oh, look, ethane. Molecules rotate. They're not glued on a piece of paper or your screen. And they have what's called stereochemistry. You notice my hand, you can know they're the palm and the back. How do I know that? Well, it's got stereochemistry. How it exists in 3 dimensions, I can see. Well, it turns out molecules exist that way. That's quite important in our body. And the term we use to discuss that is chirality. Quick check. Everybody see chirality on the screen, chap? Thank you. All right. You should know chirality means handedness. Chiral or chirality. Chiral means handedness in Greek. Now, about 2 or 3 years ago, I was teaching organic, similar to Chem 170 at COD, where I teach College of DuPage, and I had 2 students who spoke fluent Greek. And guess what? Chiral means handedness. And now I know it's just not only in the book, but I was told firsthand by 2 people who speak Greek language, it is chiral. And chirality, handedness, your hands are chiral. I'll teach that today. Notice I have 2 hands, and I can tell my right from my left. Hopefully you can too. Why? Because they're chiral, they have handedness. Ooh. And let's take a look at some stuff about chirality. Now, when we talk about chiral and chirality, I have to talk about mirror images. How many of you ever taken your hand? Ooh, homework assignment for all of you. I'm going to assume all of you have access to a mirror. If not in your home, at some restroom that you might visit, but most people have a mirror in their bathroom. Put one of your hands up and you'll see a reflection. And that's called a mirror image. By the way, I have to do it. Everybody know what that is? Spider doing push-ups on your mirror. That's a G-rated joke. Anyways, if you put your hand up to a mirror, you'll see a reflection. And that's called a mirror image. There are 2 types of mirror images, and you should know. The first one is called superimposable. And that's an image that all points coincide when 2 images, the image and the actual object, are laid upon each other. Now, the other side, wait a second, I need to do something with this slide. The other type is a non-superimposable image. And those are object and its image where not all points coincide. In other words, it's not superimposable. Now, on a very serious note, I have to give you a warning about what's about to occur in this chapter. That is, Dr. White's going to do some artwork, and I have no intention of ever going to art school, even though my mother was a very good amateur artist. Not one iota rubbed off on Dr. White. So feel free to laugh your head off at any of the things I draw now. It's allowed. Now, let's take a look at what this means. If I were to take a sewing needle here's its pointy head, here's where you put the thread. Yes, you can laugh. And I'm going to put a mirror like this as a dotted line. And if I drew the mirror image, I wouldn't have this line at the bottom. It would look like what I just drew. And these are superimposable. because I could pick this up and it would superimpose on that. And let me give you an example in real life. Is there a fake life? I like how I always use real life, non-real life. But anyways, here I have these models. If I took this model and here's my mirror, what would I see? This. These are mirror images of each other. Now, are they superimposable? How do we find out? Well, if I were to lay them like this, and if I were to push them together, the silver lines up with this silver, the back silver right here, these two tubes I have sticking up, these two black, and these two black. If I push, the center black would do, so they'd be superimposable. So this would be a non-superimposable mirror image. Now, non-superimposable mirror image, I can do real quick. My hands. Here's my right hand. This is what I want you to do tonight, or sometime today. It's your homework assignment. Ooh, I'm getting tough on you. Here's your right hand. You'll see in the mirror, it will be your left hand. And if I were to take them out the mirror, right and left hand, they're not superimposable. My thumbs line up, none of the other fingers. My center finger lines up, none of the other fingers. Ooh, I don't know if you still call this my pinky. Line up, none of the other fingers. My hands are mirror image, but non-superimposable. Now, when we talk about mirror images, we can talk about objects and later on molecules, and there are two types of molecules. One is chiral or objects, chiral object. That's an object that is not identical to its mirror image. In other words, a chiral object has a non-superimposable mirror image. By the way, first or two semesters I was teaching this, students are having a lot of trouble with this till one of them said, oh, what you have on the slide isn't superimposable, it's superimpossible, which is why they were having the problem. It was superimpossible. True story. So a chiral object is an object that has a non-superimposable mirror image. An achiral, and the prefix A means without. Achiral without handedness is an object with a superimposable mirror image. And therefore, we have two types of objects. Achiral, superimposable mirror image, chiral, non-superimposable mirror image. And if I'd ask you, is this model chiral or achiral? Well, here's its mirror image. There's superimposable. As a superimposable mirror image, it's achiral. My hands, mirror image, non-superimposable. Are my hands chiral or achiral? Chiral, non-superimposable mirror image. Let's have some fun with this. All right, I'm going to do a couple, then I'll let you have fun doing them. And everybody, hopefully you can see the following question, 3 points each. Are the following chiral or achiral? First one, round rubber ball. I should have put a round red rubber ball. For those who from my generation, a famous song was Red Rubber Ball. Yes, that was the name of a famous song. But anyways, how do you do that? Well, you look here and say you have a plain round rubber ball. I'm going to put in my imaginary mirror and draw the mirror image. If I drew it right, these circles would be identical. Can I pick this up and superimpose that on that? And the answer is yes. So therefore, this is not a superimposable mirror image, achiral. Next, your left foot. Now, in class, I'd show you, but I don't think I could do that with my webcam. But if you next time you have a chance, take your left foot and put it in front of a mirror. And guess what you'll see? Your right foot. Now, are your right foot and left foot superimposable? No. No, I'm not going to draw a foot on the screen right now. You'd probably be sent to the hospital laughing so hard you break a couple of ribs, and I don't want that to happen. So your left foot has a non-superimposable mirror image called your right foot. And if it's a non-superimposable mirror image, if something has a non-superimposable mirror image, it's chiral. Can you guys keep a secret? Don't tell anybody else. But if you ever see in a description of something left or right, immediately you know it's chiral. Now, before I do some more, let's do something with all of you. How many of you ever played Simon Says when you were a little kid? You know, like Simon Says, raise your right hand, everybody. Then if they don't say Simon, then it says, raise your left hand. Up, you're out. Let's play Dr. White Says. Touch your right cheek. Come on, play with me. All right, Dr. White says, take your hand away. Dr. White says, touch your left ear. Come on, play with it. Dr. White says, take your hand away. Now, is your face chiral or achiral? Ooh. And the answer is chiral. How do I know? How do you know to touch your right cheek or your left ear? It's chiral. By the way, if you really want to do it, make a mirror image of your face. No, I don't think so. But anyways, you'll find it's chiral. If you can know right from left, right ear, right cheek, left cheek, it means your face is chiral. But you didn't know that. Now let me give you some examples. It's getting cold out there, so hopefully you found your winter gloves. All right, why don't you try this? Which of the following are chiral or achiral? Piece of white uncooked rice, your right winter glove, a mitten. Oh, I should also put here a mitten with no leather palms, a four-door car, a tube sock with no toes. How many seen the tube socks that they sell only for women? They have the toes in it. Men's never do. That's not what I'm talking about. And finally, a pair of pants with a zipper in front. You could have pockets in the back. Which are those? Chiral, achiral. Achiral, something that has a superimposable mirror image. Chiral, something that has a non-superimposable mirror image. Can you believe Thanksgiving is just around the corner? Boy, this semester go quick. Too quick. When you're done, give me a thumbs up. All right, I think everybody's done. I better get to work. All right. Remember, you can't sue Dr. White if you laugh too hard. Try and hold on to your ribs so you don't crack them. All right, let's get going. Question is, are the following chiral or achiral? All right, first of all, uncooked rice. Here's the piece. Here's its mirror image. It's superimposable. Therefore, this is achiral. Your right winter glove. As soon as you see the word right, you know it's chiral. And how else can you tell it's chiral? Well, it turns out chiral things interact only one way with other chiral things. If you try and put your left winter glove on your right hand, it doesn't fit right. All right, now, a mitten with no leather palms. Look out, warning, artwork coming up. I told you I'm not an artist. There's your mitten. If I have my mirror, here would be my mirror image. And you'll notice all I have to do is rotate this around and it's superimposable. Since it has a superimposable mirror image, a mitten with no leather palms is achiral. Now I'm going to give you maximum super warning, laugh event coming up. Next one is a four-door car, chiral or achiral. And here I have a four-door car. By the way, you can laugh your head off. Notice I have my wheels, my four doors, a steering wheel, headlights, tailpipe, rear lights. Now, if I have my mirror image, Nope, that's wrong. What's closest to the mirror you see first. So right here, I'm going to see my wheel, my doors, my wheel, and then here I have my tail light, and over here I'll have my exhaust pipe and my other tail light, my wheel, my doors, and my other wheel, my headlights. But notice my steering wheel is close to the mirror here. I'll see it here. And this would be the mirror image of the car. And remember, this is 3 dimensions. The wheels are at the bottom, and on the top, you don't see it, but you have the roof. So I can't flip this over like I could a glove. I can just pick it over like this without rotating it and see if it's superimposable. And the answer is no. Example would be the steering column is on one side here, on the other here. And when I'm done with this one, I'll tell you a cute story about me in England and how I almost got killed twice. So a 4-door car has non-superimposable mirror image, and therefore it will be chiral. And if we were at the front of a car and I said, get in on the right side or the left side, you'd know what I'm talking about. Now, time for a true story. Back when I worked for 2 Anglo-Dutch companies in the 80s and early 90s, I went to England a lot. I went to Europe a lot, period. I'd be there sometimes for a whole month. Boy, was I glad to get home, even though they put me up because of my level in the company at some of the finest hotels in England and in Europe. It was still good to get back to your home bed after 4 weeks. For those of you who've ever been in England, they drive on the wrong side of the street, or we do, depending on your view. And if you're going this way, crossing a street like this, you're going to go like that. No, traffic is coming this way. Twice I almost got wiped out. Both times I was near a Bobby, otherwise known as a policeman. He grabbed me and said, "Sir, stop." He said, "See the thing on the street? It's for you Americans. Look the other way." And I thanked him. One of them was almost a double-decker bus that wiped me out. That was in London, and another time in Manchester. And I finally said, all right, how do I stay alive? And I came up with a good plan that helped me. Whenever I was going to cross the street, I looked and found a little old lady or a little old man. If they stepped in, I knew I would be safe, or at least I'd see them wiped out first. And it always worked. By the way, the reason I brought this up is if you've ever been in a car in England, their steering wheel is on the opposite side of ours. And where the front seat passenger would sit in an English car is where we normally would have our steering wheel. And luckily I never had to drive in England. Other managers who lived there did the driving. But the first time I got in a car, and sometimes the first time I'd be over there beginning my trip in England, I'd get in a car and we come to a stop sign or a light, and I'd be going like this and have my foot on the brake because I'd think, oh, I'm driving. Thank God I didn't have to drive. I guess you get used to it, but I'm glad to be back in America when it comes to driving, even though England was a lot of fun. All right, we got 2 more to go. Tube stock. Ooh, look out, artwork again. Here you have a tube sock. Here's sort of a tube sock. Here's the sock. Here's its mirror image. It turns out if I rotate it, it's superimposable. And therefore, something with a superimposable mirror image is achiral. Now, think about it. If you have tube socks without any artwork and also no toes, you can put each sock on either foot, and therefore that shows you it's achiral. Let's go through the last one here. A pair of pants with a zipper in front, and I didn't write it down, but pockets in the back. Normally, if we're in a classroom, I'd get up and show you this. I have sweatpants on, don't look. But that's one of the nice things about teaching on webcam. You can wear a nice top and the rest is an old pair of sweatpants on, don't look. But anyways, if we were in a class, I'd be standing up in front with a pair of, say, Dockers or jeans on, and I'd say, look, when I put my pants on, my left leg went into the left side, and my right leg went into the right pant leg, which immediately tells you it's chiral. But think about if I put on my pants backward, where the zipper, instead of being in the front, was in the back, it wouldn't feel right. And I hope, and I usually tell students this when we're in a classroom, if I ever come in wearing my pants on backwards, I hope you call the paramedics because I'll need help. But anyways, that's because, why can't you put your pants on backwards? Because they're chiral. They have a non-superimposable mirror image, and no, I'm not going to draw. By the way, the zipper is also chiral. And therefore, it's good to know, and you can impress your friends, neighbors, and loved ones, that a pair of pants with a zipper in front, pockets in the back is chiral. So objects can be chiral or achiral. And I invite you next day or two, look around when you're walking around in your house and think about chiral and achiral. Now, when it comes to molecules, we have something called a chiral sensor. And a chiral sensor is a carbon. You can have nitrogen sometimes, but for this class, I'm going to stick this to carbon. A carbon atom that has 4 different groups on it. And while I'm talking to you, I'm doing something. And here, if you notice the center here, carbon. Now, the swedge tells you the C is coming towards you, the E is going away from you. A and D are in the plane of the paper. Same thing here. These are mirror images. And this is a chiral carbon because it's a non-superimposable mirror image. Do I have time? Oh, I got plenty of time. Ta-da. Now, if you notice, this is 3-dimensional. This is coming towards you. The yellow is away from you, this plane. These 2 black, which could be whatever groups, are in a plane this way. Now, here I have its mirror image. Yellow into yellow, black into black. The center, the black on top, the silver rod coming back. 4 different groups to a carbon in the center. And mirror image, if I go like this, how did I mess this up? In there. I'm out for a demo repair. Once in a while this happens. And if you look, silver at the top, black here, red, red, yellow, yellow. And if I go like this, silver and silver line up, the black and black, but the red and yellow don't line up. Now, if I take these and make the red and yellow line up, like this, notice here, black, silver don't line up. So these are mirror images, but non-superimposable. So this is called a chiral carbon. And a chiral carbon is when you have 4 different groups attached to it. And if you notice, I have that. It's a molecule that has 4 different groups, and it's called tetrahedron, the shape here, like you saw here. I haven't talked about it, but carbon in a single bond is called tetrahedral. 4 sides, the shape is called tetrahedral. And this is called the Chiral Sensor. Now, I don't have a slide for it, so I'm going to do it on the whiteboard, which I would if we were in a classroom at ECC. All right, I'll do these 2, and then I'll let you have some fun too. And let me just check. Everybody see the structures on the screen there? Thank you. All right, I'll give you time to write A down before I go through it. I'm going to steal some water, not really steal. All right, let's look at A. Now, what is a chiral carbon atom? It's an atom that has 4 different groups, 4 different atoms or elements, or a combination thereof. Now, there's a certain special thing you should remember. If a carbon has 2 hydrogens on it, it can't be chiral because it needs 4 different groups or atoms. So if a carbon has 2 or more hydrogens, it's out. If a carbon is in a double bond or triple bond, it's out. It's got to have 4 different groups or atoms. If it's in a double bond, it can't, or a triple bond. So remember, if a carbon atom has 2 or more hydrogen or 2 or more of the same element on it, it can't be a chiral carbon. Or if it's in a double or triple bond, it can't be a chiral carbon. So let's look at the following. Now, immediately, I can say, oh, look, 3 hydrogens, that's out. 2 hydrogens, that's out. 2 hydrogens, that's out. Right here, 3 hydrogens, that's out. So all I have to look at is this carbon and this carbon. Now, if we look at this carbon as a hydrogen, this is an R group, and then all of this is R prime. So hydrogen, hydroxyl group, R and R prime, 4 different groups. And therefore, I'll circle that. Let's look at this carbon. Here I have a methyl group, halogen, halogen, hydrogen, and then all of this, I'll call this R, R prime, halogen, hydrogen, 4 different things, 2 R groups that are different, and a halogen and a hydrogen. So therefore, that would be circle. All right, let's do B. Here I have, 3 hydrogens, that's out. 2 hydrogens, that's out. Well, this isn't. Oh, look, double bond. Therefore, that carbon's out, that carbon's out. Oh, 2 hydrogens. That carbon is out. We're only talking about carbons. Notice, look at this carbon right here. It's double bond to an oxygen. Therefore, it's in double bond. That's one. So the only one we have to look at is this one. And if I look at it, I'll see a hydrogen, a thiol group. This right here, 2 carbons, I'll call R. This whole thing here, I'll call R prime. So thiol, hydrogen, R, R prime, 4 different groups. And the only one you circle is there. And since we're running low on time, I'll give you one now, and after the break, we'll do another one. And the question is, circle the chiral carbons in C. Isn't it nice Dr. White shares the fun? And when you're done, give me a thumbs up. I see 1 thumb up. I see 2. I assume number 3. So let's take a look at this. We look at the molecule. 3 hydrogens. You have to have 4 different groups or atoms or combination. When you see 2 or more hydrogens, it's out. It cannot be a chiral carbon. 2 hydrogens, that's out. This isn't, this one. When it's in a double bond, those carbons cannot be. That's out, that's out. This leaves me these 2. If I look at this one, first, hydrogen, bromine. I'll call this R, and I'll call this R prime. And therefore I have 1, 2, 3, 4 different groups or atoms or combination. Therefore, this is chiral. Let's look at next door. Let me use another color. Hydrogen, iodine. These 2 carbons I'll call R prime. This thing right here, I'll call R. This is a square, not a circle. You don't have to put the colorful things on when you do this on a test, but here, therefore, that would be a chiral carbon. Hold on. and those would be the only two you circle. And that's how you do chiral carbons. Now I'll give you a few more after the break. But turns out the stereochemistry of how a molecule is set up is just like a key. Hold on, which box do I have? Ooh, this one. A key here, and if I try and put the key in the lock this way, it works. If I don't have the right orientation, the right molecule, like this, if it goes in and interacts this way, where red has to be closer to my face, yellow far away, and black and silver, when this other molecule interacts with my body and it's not, this one, A, can do nothing, or it could do serious harm, where this one, called a stereoisomer, I'll teach that after a break, is the thing that will save my life. So molecules, atoms in your, or molecules in your body are chiral, and they have handedness just like your hands, and where a right hand will do the job, a left hand won't. And that's the importance of chirality. If I look at the clock, whoa, I'm going to let you out a whole 30 seconds early for our break. I'll see you at, actually I went longer than I should have, so I should have stopped 5 minutes ago, but I didn't. Yeah, doctor, I'll let you out early tonight. Yeah, right. But anyways, I will. It's time for a break. I'll see you at 2:55. That's when the big hand is on the 11. For those of you with digital watches, 2:55. By the way, Dr. White still has all his toys. They're important ones. Some I lost and moved and gave to my nephew long ago, which I should have kept myself, but I didn't. But never let the little kid inside of you disappear. I haven't. He's always hiding in here and ready to come out. That's a good thing. All right, we're talking about chiral carbons. I said I'd share, so I better keep my word. Let's do a few more. And here's two more. Circle the chiral carbon atoms in the following. And there are two more for you to do. While you're doing that, I'm going to look up something important. And when you're done, give me a thumbs up. Oh, I saw it. Was that a little pinky up too? All right. Before I go any further, important announcement from your host, me, Dr. White. Next Monday, I will go through the fats and oils, otherwise known as the lipids, problem set. So be sure, before next Monday, I highly recommend that you go through the lipids problem set. You notice I didn't have a problem set for polymers. What would I ask for polymers? Give an example, or what's a polymer you should know how to do. Definition of a polymer. What's another one? I'll have to look and see if I have a problem set. The other one is give an example of a condensation polymer. Give an example of a product you use in your daily life that's an addition polymer. Another thing, give an example in your daily life of something that is a thermoset polymer and something that's a thermoplastic polymer. And also, what are the definitions of what I just said? Condensation polymer, addition polymer, thermoset polymer, and thermoplastic polymer. So that's essentially what I would put in the problem set, which are the kind of questions, oh, did I give them away again, that I could ask on a test. I gotta stop doing that. No, not really. All right, let's go back and look at these. Circle the chiral carbons. As soon as you know there are two or more hydrogens on a carbon, it's out. That's out. That's out. that's out. If it's in a double bond, it's out. This one, and carbon double bond to oxygen, that's out. Well, look, we only got one left. Hydroxy group hydrogen, R group, R prime, they're different. Therefore, that's the only chiral carbon. Oh, look, a ring. Mother Nature and Dr. White love rings students down. Why? Because I don't show hydrogens. But if I did, this carbon has two hydrogens. This has one, two. I'll throw in a hydrogen there. This has two hydrogens. You can see the three there. And this one has a hydrogen. Now, how do we know if a carbon's not chiral center or chiral carbon? It has two or more hydrogens, which means this is out, this is out, this is out, and this is out. That leaves us two carbons to look at. This one and this one. And if we look at this one, I have a hydroxy group hydrogen. I'll call that R, and all this, R prime, is different. Therefore, this is a chiral carbon. Now, if I look at this carbon here as a hydrogen methyl group, and then these two carbons with the hydroxyl group, and then these two carbons without a hydroxyl group. So they're different, R prime, hydrogen, methyl. Therefore, this would be. Now, what I haven't shown you, and I'll do this one, and this is the structure of glucose, which you don't have to know. I'll teach you later, but I might as well tell you now. Glucose is the most abundant sugar on our planet in nature. And I'll teach you later on why that is so. But this is called the Fischer projection. If I could spell it. And it's named after the great German chemist who came up with the idea how to do this, did a lot of groundbreaking work, amazing work in sugars and carbohydrates. That's Emil Fischer. He's the same guy who came up with a Fischer esterification, how to make esters. Either one is a lifetime. And every intersection of a line is a carbon there, carbon there, carbon there, carbon there. So it has 1, 2, 3, 4, 5, 6 carbons. Now, I happen to, normally you'll see the aldehyde like this. I drew it out like you're used to. Let's look at where are the chiral carbons. Well, this was out because it's in a double bond, and this carbon is out because it has two hydrogens. Now, where are the chiral carbons? This one. 1, 2, this carbon is 3, R group, and these right here are prime. Same thing in this one, same thing this one, same thing this one. Glucose has 4 chiral carbons. Now, something I won't ask on a test, but I haven't taught, I'll come back to this because I haven't taught you what an isomer is. But if we look at glucose, it has not 1, not 2, not 3, but 4 chiral carbons. Isn't Mother Nature amazing? Now, I won't ask you to define this or know this definition, but I will use it. You'll probably hear it elsewhere in your studies, and that's stereoisomerism. Isn't it amazing all the neat words you learned that you can impress your friends, neighbors, and loved ones with in my class? But stereoisomerism, remember, an isomer is a molecule that differs from another one only in the way it's shaped in some way. Now, stereoisomers are put together. Stereoisomers are isomers that have the same molecular and structural formula, but differ in their orientation of atoms in space. Another way of saying that is, remember, it switches off for this slide, isomers whose atoms are connected the same way, but differ in their arrangement in space. And these are stereoisomers. They have the same connectivity, center carbon with a silver, black, yellow, red, but they're mirror images and they're non-superimposable. They're different. These are stereoisomers, or sometimes called, are you ready for this fancy word? Isomeric pairs. Pair two isomers, isomeric pairs. See all the neat words we have in organic chemistry? You can give me a, huh? Now, what do you need for a stereoisomer? A chiral center. Remember the presence of structural rigidity in the molecule. What that means is, and quaternary ammonium salts are the exception where you have to worry about structural rigidity. In a carbon, it's fixed. This is fixed. This isn't going to change. Now, in a quaternary ammonium salt, because of the way the nitrogen bonding is, think of an umbrella. In a windstorm, it can go whoop, and quaternary ammonium salts can do that too. Not in a windstorm, though. So anyways, you need that, and the switch is off for this slide. All right, switch is on big time. What is an enantiomer? Enantiomers are molecules with non-superimposable mirror images. I can say my hands are enantiomers. And an example would be this molecule. So if I were to ask you, draw the enantiomer glucose, 3 points each, what do you do? Well, you draw its mirror image, because it's always going to be non-superimposable. I had a teacher when I was learning this in undergrad who would put on the test something that had a superimposable mirror image, and the answer was, it can't have an enantiomer. I will never do that to you. I ask you to draw the enantiomer of something, it will have an enantiomer. Trust me. So how do you do it? Well, I like to put my imaginary mirror in. You don't have to do this, but it always works for me. Now, I'm going to have its backbone. Now, achiral carbons, this one and this one, don't really have a mirror image you have to worry about, so you can just redraw it like this. Everybody with me on that? Achiral carbons, you don't have to worry about the mirror. If you wanted to, you could have drawn it as a mirror image. But these four carbons are chiral. Now, if we look at the mirror right here, what's closest to the mirror? The hydroxyl group. That's what you're going to see first in the image, mirror image. What's farthest away? The hydrogen. And that will be farthest away. Think about, take your hand. Remember, this is your homework tonight or tomorrow. Take your hand and put it in the mirror. What's the first thing you see? Your palm. What's farthest away, you really can't see it, is the back of your hand. And that's similar to what I'm doing now. Next carbon. What's closest to the mirror? Hydroxyl group. What's farthest away? Hydrogen. Next carbon. What's closest to the mirror? Hydrogen. What's farthest away? Hydroxyl group. And the last carbon that I haven't done, what's closest to the mirror? Hydroxyl groups. I'll see that first. That's closest to the mirror. What's farthest away? Hydrogen. And this would be the enantiomer. Of glucose. Now, one of the things I'll teach you later, because this shows stereochemistry when I teach you this, just like the car, you couldn't flip it over, because if you did, the hood would be on the street and the wheels would be sticking up, which is not realistic. When you look at, is this superimposable on this, you can only pick it up and lay it. You can't rotate it. And if you notice, if I did that, hydroxyl group on this side, hydrogen on that, immediately know it's non-superimposable. And here's some more fun for you. B and C. Draw the enantiomer of each of these molecules. Remember, enantiomer, non-superimposable mirror image. Asking you, draw the mirror image. Oh, am I nice and helpful, or am I nice and helpful? Shut up, Dr. White. Thank you, Samantha. Look out. Thank you, Alondra. And Amber, I assume you're done. Or tell me you need more time. Okay. All right, how do you do this? Well, I like to put in my imaginary mirror and I'll do the backbone. And notice down here, this is a achiral carbon, so I can draw it this way. If on a test you wanted to do this, that's okay, I'd smile, but you don't have to. Then I have my aldehyde up here, which is chiral, achiral, so you can just draw it. If you wanted to do it this way, I'd smile, but you don't have to. But now this carbon, they're chiral. Now we have to do the mirror image. What's closest to the mirror? Hydroxyl group. What's farthest away? Hydrogen. What's close to the mirror here? Hydroxyl group. What's farthest away? Hydrogen. And I'm done. If you pick it up, I can't pick it up, but if you could, remember you can't rotate it. The hydroxyl groups would be on this side. On this one, you have the hydrogen, and it's not superimposable. And over here, this would look the same way if you wanted to. So if you, achiral carbons, doesn't matter which orientation. Remember, there's free rotation around a carbon-carbon single bond like that. Now, let's do this one. Let's look at this carbon right here. It's achiral. How do I know that? It's not a chiral center because it's double bond to oxygen. So I can write it this way, or I can have the oxygen on that side, doesn't matter. And notice the carbon up here and this one at the bottom have two hydrogens, are achiral centers, and therefore I can write it this way. You wanted to put the, let me give myself a little more room. So used to ignoring those. You wanted to write the hydrogens here, OH, and the carbonyl here on this side. That's okay. You don't have to. Same thing at the bottom here. But now this carbon, this one, and this one, if we have it, we look at this carbon, what's close to the mirror? Hydrogen. What's farthest away? Hydroxyl group. What's close to the mirror on this carbon? Hydroxyl group. That's what you'll see close to the mirror here. What's farthest away? Hydrogen. And what's closest here? Hydroxyl group. What's farthest away? Hydrogen. Now, one of the things I can now show you, because we talked about stereoisomers, this won't be on test, but it's still interesting. Actually, this is more isomers, including stereoisomers. Now, if you notice, glucose has 4 chiral carbons, and the total number of isomers, both stereo and non-stereo isomers, are 2 to the n, where n is the number of chiral carbons. So for glucose, n is 4, so 2 to the 4th is 16. There's 16 possible isomers that could exist for this molecule. Mother Nature picked only one, this one, which we call glucose. And none of the others exist in your body except this one, which is quite amazing to me. that Mother Nature in her infinite abilities, amazing abilities as an organic chemist, had a molecule that you have 16 different isomers, and she only picked one. Same thing with the other carbohydrates. So that's how you draw the enantiomer. And remember, you should know this. In terms of know this, I'll never ask on a test, what is an enantiomer? It is a molecule with a non-superimposable mirror image, but I will ask you to draw it. And how do you draw the enantiomer molecule? You draw the mirror image. You ready to impress your neighbors, loved ones, and other people you know? Your hands are enantiomers, non-superimposable mirror image. They're also chiral, but so are your feet. Now, switches off molecules that are stereoisomers who are not mirror images are called diastereomers. I didn't want to confuse you. An example, this is a double bond that can be cis and trans. Cis and trans are called diastereomers. I won't ever put that anywhere on a test. All right, I just wanted to show you how do you generate a Fischer projection. Now, if you notice on the screen, I have a molecule that's 3 dimensions. Oh, look, I have one here. Red. Oh, is it invisible now? No, not really. Red, yellow, silver, black. How would I show that in 3 dimensions? And let's do this. Now, a wedge, and this won't be on a test, but I just thought I'd teach you this, means it's coming towards you. The dashed line, actually a dashed wedge, but I just do a dashed line because I'm not good at drawing that stuff, means it's coming away from you. Up and down means it's in the plane of this piece of paper. Now, if I take this and rotate it 90 degrees, and then flatten it straight out. I won't because I'll break the model, but if I could, then it would fit like on a piece of paper. And that's the brilliant idea Emil Fischer came up with. I just found out if this is laying on my tablet, my mouse sometimes works. So if I rotate this 90 degrees clockwise, what the Fischer projection would look like, and I flatten it out, on top would be S, the silver, this would be my black, here's my red, and here's my yellow, which is what I've done here, rotate it, and notice same thing here, sort of, and C, which is coming out to you. So what this really means in a Fischer projection is C and E are coming toward you, and D and A are going back. And notice how red and yellow are coming toward you, and silver and black are coming away from you. And what Emil Fischer did was a quick way by flattening it out. So even though it looks flat, in real life, the Fischer projection, each carbon is like this. Oh, by the way, I used to, but I don't anymore. I'll never put one of those 3 dimensions and ask you to draw the Fischer projection. I stopped doing that. Students had a hard time with that. Now, when we talk about chirality of monosaccharides, they use a special designation. By the way, switches off, but this is something you might get in your other classes. There's a designation called DL. And you look at the highest chiral carbon. Remember, in aldehyde, this is 1, 2, 3, 4, 5. This is not chiral. So the highest chiral carbon is this one. If the hydroxyl group of the Fischer projection is on the right, it's called D for dextrose. I believe that's Latin for right. And if it's on the hydroxyl group on the left, it would be called labose, if I'm pronouncing it correctly, don't bet on it. And then I believe is Latin for left. And let's go out into the real world. I don't know if I mentioned this to you. For many decades now, and Dr. White's used them for many decades, the best chemical company in the world, and especially the United States, to buy small amounts of chemicals up to a couple of pounds. If you wanted to buy 10, 30, 40,000 pounds, you don't go here. But if you're looking for 50 grams, a pound or two, you go here. It used to be Aldrich Chemical Company. They got bought out by Sigma. It's called Sigma Aldrich, and they're located in Milwaukee, Wisconsin. And they are by far, in the whole world, the best company to get small chemicals from, small amounts. And they have a website they used to send out before the internet, great catalogs. I had one always on my desk. And let's go to the United States one. And if I put in here glucose, you'll see right here, alpha D plus glucose. Let's forget about the alpha. The D tells you, oh, wrong thing, right here, D glucose. And let's go to this one, D plus glucose. And this tells you the hydroxyl group on that carbon is that enantiomer or that isomer, D glucose. Here's another way of writing it. I'll teach you later today or on Wednesday. And they have various things. And if you look here, you can see the price of it. And they normally, for this one, if you do under information, you can also see the MSDS sheet. And let's see, this is super high quality glucose. If I go to less high quality, which is still good, you'll see it's quite expensive. Half a gram is $28 almost, but this is very high quality analytical standard. They have cheaper stuff, they have different qualities. Now notice the D, and again, this switches off, but this might be in your other classes, the DL, and that's that. Now, years ago, let me do one more. Now, it turns out, when we talk about enantiomers, they're very amazing molecules. Just like your right and left hand are mirror image, it's non-superimposable chiral. You can't put your left glove on your right hand. It's not going to fit right. Same thing here. I can't put my right glove. By the way, for those of you who play baseball, Remember how you have a mitt? I don't know if you had a mitt when you were a kid, but I did. Boys do. And that was for league hardball baseball. And if you were right-handed, you had your glove on your left hand, and there were special only left-hand mitts. And if you were left-handed, which I'm ambidextrous, but I'm right-hand dominant, you'd have a glove for your right hand. And you go get your glove, and they'd ask you, what are you, right or lefty? You said right. Oh, you need a glove for your left hand. And they don't fit equally on either hand. It doesn't work. Well, enantiomers are like that. Now, here's the very interesting thing. All enantiomers have the same physical properties, boiling point, melting point, other things, except for two things. One is optical activity, and the other is how they react with other chiral compounds, which turns out to be very important. Now, what's optical activity? Now, optical activity, let me do a little background, switches off for this. Now, if you look up, or over here, I have my light bulbs. If you look at the light, or if you look outside, if the sun was out, you've got light coming towards you. You can see it with your eyes. Now, light consists of waves, and also particles, but let's think of it as waves. And there's a wave coming at you at this angle, at this angle, at this angle, and this angle. And it turns out chemists or scientists, physics uses too, can put a filter in there so one wave just like this comes at you. And that's called optically active light. Hold on one second. I just started to get a Charlie horse in one of my legs, sitting too much. That's the one good thing about teaching a classroom. I don't get these. But anyways, how many of you have ever seen polarizing glasses, sunglasses, the polarized sunglasses? And they really block out light because they block out all the waves except this one to get your eye. Well, we can do that. And we can have a machine that you can put a sample and put one wave of light through that sample and have a detector on the other side. And that way you can see, does that sample, if it's coming this way, does it rotate the plane of light either direction and how much? And that's a very important way of identifying purity of enantiomers. An optically active compound is a compound that rotates plane polarized light either to the right or the left. And when it rotates it to the right, it's called dextrorotary, and it has a plus sign in its name. And when it rotates to the left, it has a minus sign. If we go back to Aldrich, nope, let's try this again. Hang in there. There we go. If we go back to Aldrich, notice it says D. Everybody see D-glucose on the screen? Thank you. You'll see D tells you the hydrox group is on the right. Then you'll see plus, and it tells you it rotates plane polarized light to the right. And then glucose, the structure. And years ago, when I was teaching this, I had someone who was a nurse in my class, Chem 170. She needed organic chemistry to get her master's degree in in nursing, because it had been so long since she took organic, they forced her to take it again. And she said, you know something? That's why it says D plus glucose on the bottles we use to feed patients. And in hospitals, if you can't eat, one of the ways they give you nourishment is they give you an IV and they inject into you D-glucose solution. It's plus D-glucose. Now, when I look at a molecule, simple monosaccharide, I can tell if it's D or L by where the hydroxyl group is in the Fischer projection. However, there's no way I can look at a molecule and see if it's plus or minus, how it rotates plane polarized light. You gotta go into the lab and measure it. It's always interesting how students think, well, why can't you do this? Well, you can't. Shh, don't tell anybody. I'm gonna do something totally on Dr. White, characteristically of me. This is a good time to take a break. I'm gonna let you out a whole 2 or 3 minutes early. Don't tell anybody I'm cheating you out of time. And with that, I'm gonna say, I'm done for today. Gang gesund. Don't forget, if you have any questions, come to my office hours or stick around after class today. If you have any questions. And with that, I'm gonna say, gang gesund, goodbye, be healthy, stay safe, it's dangerous out there. Don't forget to wear your mask, wash your hands. And I don't know if you saw Dr. Fauci today, but he was saying on interview that our wonderful president's reluctance to start the switching handover of power can affect how the virus, not to cure the virus, what do they call it? Got a mental break now. The vaccine, it will slow it down and cause more people to die. Great. But anyways, be safe. With that, I'll say goodbye. Gang gesund. See you on Wednesday.